Now, as I've mentioned before, ISE is a pretty involved piece of equipment in your network. There's a lot of things to configure, a lot of tweaking, a lot of tuning that you have to do. And what we're going to take a look at in this lesson, which is the final lesson of this module, is Identity System Quick Start. Basically, give you guys an understanding of some of the basic configurations that are necessary to get things like 802.1x running and monitor mode using a native Windows supplicant. What do we do on the Cisco switch to act as the authenticator? And what do we do on ISE to set up the basic authentication server functions? We'll talk about in this lesson how to configure the switch for AAA. We'll take a look at the radius and 802.1x components as well, and then the configuration of local users and network access devices in ISE. And then we'll look at ISE and 802.1x configured in monitor mode. And then we'll build on this as we go on to future lessons. We will build on to this discussion by looking at some of the more advanced configurations as well. So we're going to talk about how we log into the ISE platform, describe the organization of the ISE GUI, the graphical user interface, how to use internal user database on ISE. Later on, we'll learn how to integrate ISE with LDAP and Active Directory. Describe our NADs, which is our network access devices that allow us to act as authenticators. The default authentication policy that exists in Cisco ISE. We'll take a look at 802.1x Authenticator configuration procedures. Describe basic global AAA settings. Describe how to configure radius peering if we want to incorporate additional radius components. Take a look at the 802.1x global and port settings for monitor mode, the Windows native supplicant, and then describe how to verify both authentication on the ISE platform as well as authentication on the switch itself. All right. All right. The GUI, the graphical user interface, is essentially the primary way that we actually configure and administer the ISE platform. You access the GUI using HTTPS, and then, of course, prior to logging into the GUI, you have to have the basic configuration settings. There's in the CLI, when you boot up an ISE appliance for the first time, there's a basic wizard that you walk through. It's like a setup script that allows you to identify, DNS, NTP, gateway IP address information, and so on of the ISE platform. Very, very basic command line interface that allows you to get the basic configurations established for ISE before you can access it through the GUI. There are separate administrator accounts for the CLI and for the GUI. The setup script allows us to define those two accounts. We can actually establish identical credentials for those accounts as well. All right. But any changes to the account after that initial assignment do not automatically get reflected to the other account. So if I change the CLI account login information at after the establishment of the accounts through the initial wizard setup, that only affects that account. It doesn't affect the GUI account as well. If you want to synchronize or keep those identities synchronized, you have to change them both manually. All right. So you just simply go to the URL of the platform. You can access it through the IP address. You don't actually have to type in the admin/login.jsp. If you just simply go https:// and then the IP address of the ISE server or ISE appliance, then you'll be redirected to that URL. That's basically the default URL to log into ISE. All right. And we're going to be doing some labs a little bit later on. Maybe not today, but first thing tomorrow, we'll probably jump into a couple of different labs where you guys get to configure this stuff. All right. Now, once you get in, the GUI itself has essentially 4 major functions. You've got your home screen, which is like your little dashboard, and it can kind of give you the status of the platform, what's going on with the platform at that particular time, how many guests you have, how many total endpoints have been authenticated, how many profiled endpoints, posture compliance, etc. Just like any security appliance, we have the GUI that provides us that functionality. And then we have different operations. We've got an operations menu, basically monitoring, reporting, troubleshooting tools, etc. You've got a policy menu. Policy menu provides really everything that you essentially do on the system, right? All of the ISE policies, authentication, authorization, profiling, posture assessment policies, and so on. And then you have your administration menu, right? Basically providing configuration components for the actual ISE deployment relevant parameters, right? Licensing, certificates, backup and restore. This is where we also add all of our network resources, our radius server sequence, external radius servers, and so on. So basically the components that the platform itself is going to use to perform all of its policy functions are going to be defined under the administrator screen as well. All right. In ISE, we have the ability to integrate with Radius as a backend server not Radius, LDAP, excuse me, as a backend authentication credential data store. But we can also maintain a local data store, what we call internal user database, which is a very easy way for us to provision users internally, right? That provides us a way of having kind of a basic repository of users. Initially, you may want to deploy ISE in this way. That's typically the way that we will deploy ISE. We'll implement some of the most basic functions first, test the validity and test the functionality of those particular functions, and then start to layer on or incorporate additional functions beyond that after we've gone through and verified successful operations of some of those critical functions in the beginning, right? So a local user database is a way to do that so that we're not relying on integration to LDAP or Active Directory or whatnot, and having another point of troubleshooting and testing beyond that. Obviously, for easier management of user accounts, it's probably better to use some sort of external database, but we can do this internally as well. EAP-TLS, PEAP-TLS, they don't actually use password-based authentication, so the internal database itself does not support those particular protocols. Right, in that case, we need certificate-based authentication, and we'll take a look at that later on as well. All right, NADs, NADs, basically these are our network access devices. These are Radius clients. ISE obviously provides the Radius server functionality. Basically, any type of NAD or network access device is any device that performs the role of authenticators. Remember, you have three major components in the 802.1x architecture. You have the supplicants, you have the authenticators, and you have the backend authentication server. So these authenticators act as a proxy between the supplicants themselves and the Cisco ISE platform, being the authentication server. They're responsible for enforcing authorization policies like VLAN assignments, downloadable ACLs, etc. We apply those to these network access devices as well. ISE decides whether the client traffic should be permitted into the enterprise network, what different enforcement mechanisms are applied, but ISE doesn't actually facilitate that restriction, right? It simply defines the policy. It might even store some of the policy parameters like downloadable ACLs and whatnot, but then it pushes out those policies to the network access device, and the network access device is then directly responsible for implementing and enforcing those options. Could include dynamic VLAN assignment, downloadable ACLs, the application of security group tags, and so on. All right. Some different types of network access devices could include your switches in your network, ASAs, wireless LAN controllers, and so on. All right. A lot of the settings, as you can see here, are optional. There are very few settings within the actual NAD configuration that are required. You can tell what's required with the little asterisk symbol next to the configuration. Some of the other components are not necessarily required. You guys are going to be doing a lab exercise where you're going to be setting up these various components in the lab. You're going to be adding a switch, for example, as a network access device. The device name, the IP address, the network device group settings, these are all required settings based on the asterisks that you see there. But things like SNMP, the security group access parameters, which is used for TrustSec, these are all optional, and it just depends on what you're doing in your enterprise as to whether or not you decide to actually configure these components. The actual network device groups can be helpful because you can actually identify different types of device groups in the organization, and then based on that association, apply different properties to those device groups. ISE actually utilizes two different device group hierarchies, device type and device location. And then based on that, based on those components, we can apply different parameters to the devices themselves. All right, so we'll take a look at that a little bit later on and see how that plays into the role of configuration by assigning the device type or the device location a little bit later on. All right. Once you've gone through and you've identified all of your network access devices, the next step would then be to go and identify your different authentication policies. The authentication policies are basically the set of rules that allow us to not only identify users and endpoints, but then identify what we do once we've identified those particular users and endpoints. Authentication requests get processed as soon as the endpoint attempts to access the network through the Authenticator, the network access device. ISE is going to evaluate that access path. Basically, where is the network device attaching itself to the network? What are the credentials that are being applied or supplied by that device? And then we're going to go check our identity store, whether it's a local identity store or a back-end LDAP identity store. And then we have an authentication policy that goes through several checks and then makes decisions based on those checks. So we're seeing here under policy, under authentication, that's where we're identifying the different policies. Makes sense, right? If you look at the menu here, you've got policy and then you have authorization, which is post-authentication. You got profiling parameters that you're going to set up. You've got posture assessment parameters. And then for BYOD, we've got client provisioning options. And then for Cisco TrustSec, our security group access policies. And then our policy elements, which is basically a dictionary of all of the elements that are going to be included as part of our a reference from authentication or authorization and so on. All right. We'll get into configuring each of these elements a little bit later on. All right.
You know the current ISE is completely different.
Yes. Yeah. Well, it is completely different. I mean, the framework is still there. The layout is completely different. It looks more like the standard unified communications type of layout, right? Unfortunately, this course was printed in 2014, so we're looking at the 1.3 version of ISE instead of the latest version. But all the components are still there, right? They're just laid out differently, right?
Right.
Yeah. So visually, it's going to look different, but the overall concepts are still the same. All right. So everything we do is in this this portal, right? We go under policy, we go under authentication. Basically, what we're establishing in this particular case is all the different checks that define basically our decision point on how we're going to apply authorization. Remember, authentication is just the first step in the process. right? The authentication policy has all of the different criteria based on how we're going to validate the user's identity, what devices they're attached to. Are they coming in over the physical wired network? Are they coming in over the wireless network? And then based on those different criteria, we perform the actual user identity against our identity source, which can be an internal identity source or an external identity source, or it could be actually a sequence of different sources, right? We can say, okay, check internal first, then check external and 1 versus external 2 versus external 3. The authentication policy defines the protocols that ISE is going to use to communicate with the network devices, the identity sources that need to be used for authentication, and then whatever conditions that need to exist in order to obtain some sort of result, whatever that result might be. Whether it's we're going to authenticate, we're not going to authenticate you, and so on. There are two types of authentication policies that exist in Cisco ISE: simple authentication and rules-based authentication. Simple authentication doesn't use any conditions, and usually it's not something that we're typically going to use within the ISE platform. We're basically using primarily rule-based authentication, where we have a set of rules and then each rule defines conditions, and then whatever the resulting action is based on those conditions being met. The actual rule-based authentication is the default and more commonly used component in ISE. And probably the best way to understand that would be to look at that from a configuration perspective when we go back and do our lab exercises. You guys are going to be setting up these different rule-based authentications. There are some pre-canned authentication rules by default. We don't necessarily have to tune the policy if we're going to use those basic canned scenarios, but if we have specific requirements within our organization or within the enterprise, we may have to tune those policies or copy them and edit them to meet whatever specific requirements we have based on our authentication rules that we are going to use, right? You can see the example, the three example or default policies that exist here. MAC authentication bypass over wired or wireless networks using internal endpoints. .1x authentication, wired or wireless .1x authentication using default network access. And then finally the default rule, if there is no match, what are we going to do based on that? Now we don't see the rule details here. You'd actually have to come into these arrows here in the edit conditions to be able to see specifically how we're applying these authentication rules, and then based on those authentication actions, what happens as we move into the authorization piece. But we'll see that later on. We'll see the specifics of that later on. Okay. In order for us to deploy 802.1x, we need our authenticators, right? The network access devices that actually provide the authentication function. So we have to set up a few things initially before we then go back into our network access devices and configure the authenticator function that we're going to see. We'll see that on the next couple of slides. First thing we need to do is we need to set up our global AAA parameters, which would include things like the default group .1x authentication parameters, the authorization parameters, the accounting parameters. And then we have to configure our radius association. And then finally, we have to configure our 802.1x settings on the switch based on the physical ports that are actually going to be providing the .1x authentication. All right. So we have a couple of options in that regard. We can enable .1x globally, or we can actually configure, well, there are some global configurations that need to be applied regardless, but then we can also apply some specific interface, 802.1x interface specific components as well. Are we going to do authentication open? Are we going to do monitor mode? Are we going to do low impact mode, closed mode, etc.? Are we going to, what's the port-based ACL that's going to be applied in our low impact mode, which is that default ACL that gets applied in when we're not doing closed mode or even downloadable ACLs. Are we going to configure MAC authentication bypass? Are we going to do any kind of optional tuning? We won't see all the specifics of this initially, but as we move further into the course, we'll see more specifics about each of the individual configurations. Before we can actually get into the specific AAA configurations, AAA needs to be applied globally on the switch itself. We use the AAA new model command to be able to enable these global functions. By default, Cisco iOS devices don't have AAA new model established, so we're going to execute the global configuration command AAA new model so that we can have all of these other AAA options available to us in our configuration scenario. Otherwise, those other AAA commands won't exist. All right. Now, AAA servers can be logically organized into what we call server groups. Group radius is an example of a AAA server group that's defined by default and includes all of the radius servers that are actually configured on the switch. We don't see the specific radius server configurations here. We'll see that in the next section when we look at radius peering. That's where we actually go in and define the actual radius servers themselves. But group radius basically automatically includes any defined radius server in the radius peering configuration, which we'll see next. It's very common, and I think that most people tend to use this configuration to simply reference the group radius in the AAA configuration commands and then define all of our radius peering options, individually for each of the radius servers that are involved in that process. All right, and we'll see what that looks like in a couple of slides here. All right. All right. We use the AAA Authentication.1x group default group radius command. That's the first command that you see here. Oops, sorry about that. Right here. The AAA Authentication.1x group radius command, global configuration command again, that defines the authentication method that's going to be used by default on the switch ports. We don't necessarily have to use the default method list. .1x, of course, applies to the fact that we're going to be doing .1x authentication. Default is the group name. We could specify a different group name if we so chose to, but then we would have to identify that group specifically on each interface. And then this is the method actually that we're using. In this case, group radius is the actual, we're going to use our radius configuration to provide for the authentication. All right. The next command that you see there, configuring the default AAA authorization method used for network access by the authorization method, I should say, by saying AAA authorization network default group radius. Basically what we're saying in this case is let's go ahead and rely on a radius configuration to identify the authorization profiles that are going to be applied to the clients that are connecting through this particular switch, right? We configure the switch to facilitate all of the radius authorization, 802.1x, per user ACLs, VLAN assignment, and so on. Anything that ICE can push down to the switch is going to come from ICE through the radius messages that get sent back and forth, the AV pairs that we send back and forth. Then the final command, the accounting process, AAA accounting.1x default start stop group radius. Another global configuration command causes the switch to send radius accounting messages whenever a radius session starts and also when the radius session terminates. These methods are all called the default method. Default indicates that the method that's going to be used if we don't actually individually specify a specific method on the interface itself. You may have scenarios where some ports might use one kind of method, whereas other ports might use different types of methods for authentication, authorization, etc. So you might have to create custom method lists that are not called default, but for most implementations, the default method list is pretty much adequate for what we're trying to accomplish in our configuration. So at a minimum, this is what we're going to configure globally. Now the next step in this process is to go ahead and configure our radius peering, where we're actually able to identify the specific radius server components. Configuring the radius server using the radius server host address, the authentication port and accounting ports. You can specify those if you choose. If you don't specify them, then it will just simply use the default values, 1812 and 1813. As I mentioned previously, 1812 and 1813, those are the default ports that ISE is going to be configured with. You may decide to change the port numbers for just a kind of a obfuscation or an additional layer of security. And you can do that in ISE. You can change the authorization port, authentication port, and the accounting ports if you want to, although it's not generally done. But that's what that command allows us to identify. What is the IP address of the ISE server, and what is the authentication port and the accounting port. By default, the ports that are used by ISE would be 1812 for authentication, 1813 for accounting. We then can configure the interface from where all radius traffic is going to be sourced. We see that as the very first command in the list here. The reason why this might be particularly important is because you can have access rules defined in the system that identify where radius traffic is supposed to come from in order for it to be sent over to the radius server. Well, generally speaking, if a router is generating traffic or a switch or whatever type of device is generating traffic, the source address of that traffic is usually the exit interface that's used for generating that traffic itself. So we might have to specify the source interface for a radius traffic. If the traffic's already being sourced from an interface that you've identified, then it shouldn't be too much of a problem sending that traffic to its destination without this command. All right. All the traffic's going to be sourced in this case from interface VLAN 100. If the switch, like I said, consistently uses the same source interface, then we don't necessarily have to have this configuration as part of the configuration. The IP address of the source interface is the IP address that is configured for the NAD in ISE. So that's really important. In order for ISE to be able to accept messages from a network access device, the source address of that traffic has to come from the address that's configured in ISE for that particular endpoint. So by specifying the source address, you're essentially guaranteeing that that's going to be the case. All right? So we configure the interface from where all the radius traffic comes from by using the IP radius source interface command. In this case, VLAN 100.
If you don't specify that, I think it actually comes from the lowest IP address.
Well, it depends, right? It depends on how the traffic is exiting the device itself, right? Generally speaking, switches and routers will always source traffic from the exit interface. So if ISE happens to be, for example, on a different VLAN than 100, and I'm communicating to that server over that VLAN interface, then the traffic is going to be sourced from that particular interface. Does that make sense? So yeah. It may not be the interface that we specified in ISE, which means that that traffic is going to be denied. All right. Now we can.
I had problems with TACAC's login onto a switch because it kept forcing the traffic from the wrong interface.
Exactly, and it's when you add a client to the TACAC server, you're specifying the IP address of the client that you're going to accept those TACAC messages from, and if that doesn't match, then it's just simply going to ignore those particular messages. Absolutely. All right. Now we also have the ability to specify the dead criteria. Basically, there's two different components to this, the time and the tries. We see the actual command right here, radius server dead criteria time 30 tries 3. The time is the time in seconds where the switch does not need to get a valid response from the radius server. anywhere from 1 to 120 seconds in this particular case, whereas the tries is the number of tries, or the number of times, excuse me, that the switch, if it doesn't get a valid response from the radius server, before it actually considers that the radius server is no longer available. And that goes from anywhere from 1 to 100. So we're saying, okay, we're setting the time to 30 seconds, meaning that we don't need to really get a valid response from that radius server within that 30-second window. And then the number of times that the switch, in this particular case, before it considers that the radius server is no longer valid, is going to be three times. All right, so that would be 90 seconds in this particular case. All right. Not all radius attributes are used in the radius server, it depends on the scenario, of course. There are some attributes that ICE uses specifically in 802.1x that are actually not enabled on the switch by default. So that's what we see in the next two lines here, representing, oops, not that line, this line right here, radius attribute 6, and this line right here, radius attribute 8. The radius server attribute 6 on for login auth, that command sends the service type attribute in the authentication request. ICE uses that service type to distinguish between .1x supplicant logins and MAB processes, like MAC authentication bypass processes. And then radius server 8, include in access request, causes the switch to include the endpoint IP address in the authentication request. The IP address is then carried over to the ICE server in the frame IP address radius field. Well, you know, we talk about attribute 6, we talk about attribute 8, attribute 25. Like you said, you may or may not have to implement these specific attributes. With radius, we talked about this in one of the previous lessons, but I'll go ahead and hit this up again. The attributes are defined, well, they're used to pass information to ICE that are specific to authentication, authorization, and accounting elements that are part of the radius architecture, I guess, if you will, for lack of a better term, right? What we're seeing here specifically are what we call VSAs, right? These are vendor-specific attributes as opposed to, say, like an IETF attribute, which would be defined as kind of a standard attribute in the radius process, right? Those attributes, the IETF attributes, there's 255 standard attributes that are used to communicate AAA information between the actual client and the server. Pretty standard attributes, so you can pretty much assume that these attributes are going to be part of the process, or already automatically included in the communication process between the authenticator and the radius server anyway, right? These are just standard attribute data is predefined, etc. All clients and servers that exchange AAA information using these IETF attributes work just fine, and you don't typically have to do too much with these particular attributes. It's when you get into some of the more specifics, like attribute 6, attribute 8, attribute 25, and so on. Or Andy, like you were mentioning this one that you couldn't recall, but it was specific to a particular application that you're running in the network. Radius vendor-specific attributes, they're kind of derivations of the IETF attributes. For example, attribute 26 allows a vendor to create another 255 different attributes that don't match the data of any of the IETF attributes, but then they get encapsulated behind attribute 26. All right. The way that the radius packet is formatted is you got some sort of code. The code is going to identify what type of radius packet it is. Is it an access request, which would be a code 1? Is it an access accept, which would be a code 2, access reject, code 3, and so on? Is it an accounting request or an accounting response? Those would be code 4 and code 5. But in the identifier field, this is an octet to match requests and response messages that are going back and forth between the client and the server. Then we have a 2-octet field, that's the link field, and so on. Lots and lots of different packet types. And we don't have to get into the specifics of the attribute, the service type, the integer, and so on. It's way beyond the scope of what we need to know for this class. But like I said, there's over 255 different attribute types that are defined in the IETF standard, and then we have some specific ones that Cisco has defined. All right. Attribute 6, like I said, it's a service type attribute, and the on for login, off. Basically, this identifies the type of service requested for the type of service that's being provided. I don't know if that makes sense, but login would be make a connection. Exec user allows me to identify or start an exec session. And then there's outbound, administrative, and so on. We don't have to get into the specifics of that. And then we have attribute number 8, which is the framed IP address attribute. This is going to tell us the IP address that to be configured for the particular user. And what happens is we send the IP address information of the user to the Radius server in the original access request message. In this particular example, this may not be something that you decide to do in your own environment, but in this particular example, they've decided to add this attribute by using the Radius server attribute 8, include in access request message, right? You look at the 25. 25 is a class attribute. You know, we have different kinds of attributes. We have service type attributes and NAS attributes and so on. This happens to be a class attribute, and it's an accounting component, basically saying, hey, I want to include all the accounting packets for this user supplied by the Radius server. So access request include identifies that. Again, these are non-default attributes, and whether you decide to enable these attributes or not will completely depend on your specific environment, right? What you're configuring in your environment. All right. Radius server VSA send accounting configures the switch to include vendor-specific attributes in the accounting updates. And then Radius server VSA send authentication configures the switch to include vendor-specific attributes in the authentication process. And then we also have IP device tracking, which allows essentially ICE to track endpoint IP addresses that are, this is a global command, but it would apply to any .1x enabled port on that particular switch. All right, you do need to do this command in conjunction with the attribute number 6. You can't do device tracking if you don't include attribute number 6, which is the login authentication piece. All right. It's difficult to say what you would decide to use or not use in your own environment. It just depends on what your overall objectives are in your configuration. All right. Before 802.1x can function on a switch port, it has to be globally enabled on the switch. That's the .1x system auth control command. Pretty simple, just turns on the feature and allows us to start configuring .1x on the particular interfaces. All right, then we go into the interface. In this particular case, the interface is in Access VLAN 10, Voice VLAN 9, not really related to .1x, but we are doing multi-authentication. Host mode is multi-auth. And if you recall, that multi-authentication allowed us to authenticate the phone and the PC. and we're doing authentication open in this case. By default, 802.1x drops all non-ePOL traffic before you actually successfully authenticate using 802.1x, or if 802.1x is not going to work, MAC authentication bypass. So this mode, which is the default, is closed mode, meaning that the door is closed until you're actually authenticated. By putting in authentication open, we're changing that behavior. It basically enables open access mode, which allows all kinds of traffic in both the data and the voice VLANs before any successful authentication occurs. All right. If the traffic is not restricted by a particular access list, in this particular configuration example, we don't see an access list applied to the interface, then the traffic is just simply allowed, right? There's no restrictive ACL locally assigned to the port. And this is what we define as monitor mode. If you do have a locally assigned ACL in place, not a downloadable ACL, but an ACL that was actually predefined and pre-configured, that's what we call low impact mode. That's a distinction that you'll probably have to know for the test as well. We could enable MAC authentication bypass on a port by using the MAB command. Keep in mind that 802.1x is still applied to this interface, and MAB would only be used if I wasn't seeing any ePOL messages from the client itself. And then we can also configure the authentication priority using Authentication Priority command. That's an interface-specific command to say, I'm going to go ahead and prefer 802.1x over other authentication methods, right? So we see the authentication priority in this particular case, .1x is going to be preferred over MAC authentication bypass. And then we specify the order as well, .1x over MAB. There was last time I taught this class, there was kind of a discussion about what the difference is between priority versus order, right? When you're setting up the authentication priority, we're identifying essentially which, if the client supports both authentication methods, which method are we going to prefer over the other? And in this case, .1x would be preferred over MAC authentication bypass. We can also specify the order for the port using the authentication order command. In this case, we have .1x followed by MAB. Usually we want to identify that we're going to use 802.1x first, followed by MAB. But there may be a scenario where MAB is essentially the primary method, and then 802.1x would be the secondary method. Would be, based on, what's happening in your particular. All right. There is potentially a little bit of confusion as to the difference between priority and order. Let me see if I can't maybe come up with a better description than what they have in the book. The book doesn't really get into the specifics of it. This is defined as what we call flexible authentication, right? Flexible authentication is essentially where you as the administrator are defining the sequence and the priority of whether I'm going to use 802.1x, MAC authentication bypass, or what we call local web auth. We haven't even identified that component of it yet. By default, the switch is always going to attempt .1x authentication before it does MAC authentication bypass. But with flexible authentication, or what we call flex auth, we can change that order so maybe that MAB is attempted before any 802.1x authentication is attempted. There is a consequence to making this particular modification, though. If we change the default order, all endpoints, including the endpoints that actually can perform .1x authentication, are going to be subjected to MAC authentication bypass. So that's going to generate not only additional authentication traffic on the network, but it could potentially delay the authentication process as well. So there are essentially three different commands that apply to, well, two commands that apply to FlexAuth, which we see here, right? The order and the priority. The order sets the order of authentication method that's going to be used on the port, and the priority sets the priority of the authentication methods used on the port. But then we also have fallback authentication methods as well that we can specify. What are we going to do if the authentication fails? Do we simply use the next configured authentication method, or is the port going into an unauthorized state automatically? We don't see that command here. That command, you guys may or may not be implementing this in your environment, but it's called the Authentication Event Fail Action command. And we have two choices there. We can either do next method as the event action, the event fail action, or we can do an authorized VLAN, meaning that we're going to put you into an authorized VLAN, and then we specify the VLAN ID. Let's talk about some scenarios, right? Because this scenario is pretty standard, where .1x is preferred over MAC authentication bypass. It's kind of the default, actually. The priority changes, though, if you actually change the order. So, for example, if MAB is configured as the first authentication method, then MAB will automatically have priority over all other authentication methods. So if the port is configured to attempt MAB before .1x, then by default, any device that passes the MAC authentication bypass will never be allowed to pass a .1x authentication. All right, so if an endpoint, for example, needs to perform .1x authentication, it would actually have to fail the MAB process first. So that means the MAC address cannot be in the MAC address database that's checked for MAB. And additionally, the authentication, the authorization, etc., should not have a policy that allows unknown MAC addresses to pass MAC authentication bypass, right? Maybe if we're putting somebody into a guest VLAN or a dynamic VLAN. All right. Another case that you might run into this would be if, what happens if 802.1x fails, for example. We can either configure two mutually exclusive options for 802.1x failure. One is to go ahead and do the next authentication method, which is called, quote unquote, the next method. Or the other option is to authorize the user for a specific VLAN if the authorization fails, like an auth-fail VLAN. All right. If we're using the next method option, and that's configured and or even potentially a third authentication method, there's only three potential authentication methods that exist in ISE, right? One is 802.1x, the next is MAC authentication bypass, and the third is WebAuth. If none of those options work, or if they fail, then we'll basically return back to the first method. In the case of our example, MAC authentication bypass. If MAB fails again, then .1x will be used, and it will fail again. The device will never get any kind of access because it's going to continually go through this process. All right. The downside to this is that MAB cannot be used to remediate known devices that fail .1x authentication. What do I mean by that? Because I've run into this scenario in a configuration with a client where we've got this, what do I do when I fail? Go to the next option, and then we get caught in this recurring loop of authentication, right? So let's say, for example, an employee PC that has an expired certificate. It's not gonna be able to pass 802.1x authentication in that case. 802.1x authentication is going to continue to fail. The next method, remember MAB was the first method, is WebAuth. and we're just going to continue to cycle through those failures. All right. That's if you're using, by the way, that event fail action of next method based on the methods that you've defined. Unfortunately, the book doesn't really get into the details of this. So I think it's really important to understand, because you're going to run into a scenario where you have to define what happens if it fails. All right. I'll take a look at some of these other options, but there are a couple of things that you should probably do, even though this particular slide doesn't show that configuration, to avoid that potential looping problem. Number one, you have to specify the authentication failure behavior. Again, you have a choice: next method with local web auth, or the auth fail VLAN method. If the next method failure handling and the local web auth are both configured, if the supplicant retries .1x authentication during or even potentially after web auth, then the .1x authentication is not going to start again, even if the web auth status fails. If we have the auth fail VLAN configured, the endpoints that fail any kind of .1x authentication after they've done a successful MAC authentication bypass, they're going to be put into that auth fail VLAN, and then we're not going to attempt any other methods as part of the process. What's the bottom line here? Maybe I didn't explain it very well, but hopefully you guys understand what I'm talking about. If we see some configurations later, maybe I can kind of identify in those configurations what that configuration option looks like. But there are essentially three things that you need to remember and that doesn't apply to this particular configuration scenario, but three things to remember if you're applying MAC authentication bypass before 802.1x authentication, but 802.1x authentication has a priority. So the order is mab.1x, but the priority is .1x mab. Number one, 802.1x capable endpoints can be in that MAC authentication address database. If I use the next method for .1x authentication failure handling without local web auth, then we can see kind of strange things or weird things happening, and we can have clients that are getting this intermittent network access where we're cycling between MAB and 802.1x failures. If I want to make sure that I have deterministic behaviors, if 802.1x authentication fails after a successful MAC authentication bypass, then we want to use the auth fail VLAN, or we want to specify local web authentication. It's really confusing, but it's a concept that's often overlooked, this flexible authentication order, priority, and failed authentication process. And hopefully we'll be able to kind of dive into that a little bit deeper in some of the future lessons here. Okay? All right. Obviously, we know that whenever we have any kind of .1x configured on a port, it's going to start in an unauthorized state. While the port is in that state, it's not configured to be any part of any VLAN, voice VLAN, or whatever. It's going to block or not allow any of the ingress or egress traffic except for three things. Number one, .1x, ePOL conversations. Number two, Cisco Discovery Protocol. And number three, spanning tree. All right, so and that actually has shown up on the test as a test question in the past. But unauthorized ports do allow three types of traffic: CDP, spanning tree, and 802.1x. Once the client has successfully authenticated, the port changes to an authorized state. That's going to allow whatever traffic to flow through that port based on the authorization profile that gets applied to that port. If the port's configured for a voice VLAN, it's going to allow all of my RTP and skinny or SIP traffic, as well as the .1x packets. And if a client doesn't support 802.1x protocol, then we obviously going to have to authenticate that client some other method. 802.1x enabled clients connect to the port. If the port is not running 802.1x, the client is going to initiate an authentication process by sending the ePOL start frames. But if the port is not configured, we don't have .1x system auth control on the switch, or we don't have the .1x configuration applied to the interface, then we have to go through a process of what happens if I don't get a response, right? The client is going to repeat the authentication request messages several different times, but because we don't get a response, the client begins sending frames basically like the port was authorized. It's just going to assume, hey, this is not a .1x port. It has a static configuration. It doesn't require me to authenticate, so I'm going to start sending frames into the port. There is a command, .1x port control, and we can see in this case it's set to auto, but we have three different options. We can do forced authorized, we can do forced unauthorized, or auto. So let's talk about auto, since that's the one that's applied on this particular interface. As the name implies, the port begins in an unauthorized state, allowing the processing of ePOL frames that are sent and received through the port, and then the authentication process takes place, and we go through the different port changes based on those different ePOL messages that are received in the different authentication. The switch is going to request the identity of the client, relaying that information back to the authentication server, and then each time the client attempts to access the network, it's going to have to uniquely identify itself by using the MAC address of the client and so on. Basically, auto means we're going to go ahead and run this port as a standard 802.1x port. Forced authorized, in this case, basically disables 802.1x authentication and essentially puts the port into an authorized state without any authentication messages going back and forth, and it sends and receives normal traffic without going through the 802.1x process. This is actually the default setting if you don't put that command in. If you don't say authentication port control auto, the port is obviously automatically forced authorized. Forced unauthorized, as the name implies, means that the port not only starts in an unauthorized state, but it stays in an unauthorized state. It's going to ignore any attempts by the client to authenticate. The switch is not going to provide any authentication services to the client through that port, which means that the port is effectively disabled in this case. If a client is able to successfully authenticate, it's going to receive that accept frame from the authentication server. The port state changes from unauthorized to authorized, and then it will remain in that state as long as the port is active and the client is communicating over the port. If for some reason authentication fails, the port doesn't transition to the authorized state. Obviously, we're talking about the auto mode in this case. If the authentication server can't be reached for whatever reason, the switch can resend the request. If we don't get a response within a specific amount of time, then the switch just simply reverts to whatever the status of the configuration of the port is, either unauthorized, authorized, or whatnot. All right. When the client logs off, ePOL logoff messages cause the port to change its state from the authorized state to the unauthorized state. All right. As far as supplicants go, Windows operating systems include a native 802.1x supplicant. It's disabled by default, but you can enable that feature. So if you want to use the Windows native supplicant, Andy, thank you for providing that information. You have to have the wired auto-config service turned on. You'll notice that if I look at for example, if I take a look at my Ethernet adapter properties, before that service is enabled, I don't have an authentication tab available in my Ethernet properties adapters settings or adapter settings. So if I go ahead and enable this service and I take a look at the properties of my Ethernet adapter now, I have the authentication tab available. which allows me to specify my .1x authentication properties. So, what EAP authentication method am I going to use? And then I can go in and, of course, change individual settings for this particular authentication method. I'll turn that off for now. Yeah, that's part of the Windows native supplicant. Not sure what you'd have to do on a Mac or a Linux environment, but all right. So, but we know that there is a native 802.1x supplicant. It is disabled by default, as we just saw. And actually, the book does mention it specifically. Enable it manually by starting the wired auto config service, and then the native supplicant supports PEEP and EAP-GTC. By default, it uses PEEP with MS Chat v2 as its authentication method and is configured for machine or user authentication. All right. If a user is logged in, it will use the user credentials. If no user is logged in and it is a member of the Active Directory, it will use the machine credentials. All right. You said, Jan, you ran into that. You were unaware of that previously when you were doing your AnyConnect deployment?
Unaware of
the fact that you needed to enable that service.
Yeah, no, I didn't. It just never even occurred to me that I would have needed to. And then after many times having a machine pass verification but fail authentication, I finally found the article that said, "Oh, don't forget to turn this on."
Ah, right.
So, but it can all be done through Active Directory. So once we figured out the problem, we just deployed it to everybody.
Yeah, I was gonna say you can just force it through a GPO.
All right. We can also verify authentication on ISE. Very quick option to see if clients are authenticated in ISE by going into operations and in an authentication menu. We'll see the authentication method, the session ID, other specific details for the authentication session. And we can actually customize this menu to include additional columns or remove columns depending on what it is that we want to see in this particular table by using the Add Remove Columns button, which you can see as the second option here. This Add Remove Columns button here allows us to kind of customize this output. All right. If we decide to add remove columns, we have a whole bunch of choices. We can add, session start information, IP address information, change of authorization actions, session ID, IP address, port information, endpoint profiles, posture status, traffic statistics, and so on. Lots and lots of different options that we can add. All right. If we want to verify the authentication that occurs on the switch itself, we can do a show authentication session interface, and that will allow us to identify who's authenticated. In this case, the username is student. The session ID is listed there and highlighted in red, and the authentication method was .1x, and we were able to successfully authenticate using .1x in this particular case. That common session ID, unique ID, which is basically used as a key field to keep the representation of the session synchronization between ISE and the switch. Basically like it's just the session information for that particular connection at the time. And we'll see in the very last module, module 6 of this particular course, we're going to use some various troubleshooting commands that actually utilize that session ID information to be able to identify issues with the process, authentication process. All right. So that concludes that lesson. We talked about basic ISE configurations, 802.1x authentications, how those authenticators worked and integrated with Cisco ISE, rule-based authentication policies, the three predefined rules that we talked about with MAB 802.1x in default, how we can use authentication to give access to users based on either a local database in the ISE server or some sort of external database using LDAP or Active Directory. And then we looked at 802.1x authentication on the switch. How do we configure that? What is the radius association between the switch and the AAA server? And then finally talked a little bit about some of the other aspects of configuring authentication on the device itself. So that concludes that module. That's module number 1. What we're going to be getting into in module number 2 is really just the ISE fundamentals, right? Identifying all of the specifics of Cisco ISE. What are the key characteristics of the ISE platform? How do we enroll ISE in the public key infrastructure? What is the internal versus external authentication process for ISE, and so on. So lots of good stuff coming up in the next module. 4 different lessons about really just kind of incorporating ISE into your environment fundamentally before we start to go in and configure the individual policies and so on. All right, so we'll see you guys in that next module.